Hello, I have the pleasure of introducing Mr. Ali from Bloomberg, London. He's going to talk on computational origami. Mr. Ali.
Thank you. Great, thank you. Hi, everyone. I'm Ali. That's my full name up there. And I'm an engineer at Bloomberg. This presentation, though, is more of a personal passion project of mine. Just as a quick show of hands, who in the room has ever done any sort of origami before? Yeah, kind of what I expected. If you don't know, it's the art of paper folding, and you may have made models of animals with it. It's very popular. Sometimes you can make some really cool modular geometric structures. But hopefully today, I'm going to be able to show you origami in a new way, and that is to construct things to solve computational problems in paper folding. Taking a step back, my first introduction to origami was with one of these. It may look a little alien to some of you. It's the British version of a popular American brand. And to avoid using any British or American specific terms, I'll just say it was a thin-sliced potato-based snack in a bag. This I was a big fan of when I was much younger, and when I was finished eating these as a small child, my mother would sometimes entertain me by folding the bag in an interesting way. And she would often do it something like this: fold it into a thin strip first, and then sort of wrap it around itself, tuck in the edges, and you end up with a triangle. I've seen other people do this. It's fairly widespread in certain communities, and it's a 1-1 root 2 triangle. So that's kind of cool. Starting with one variable, the width of the strip, which we'll just say is the unit length, my mom was able to construct an irrational number, square root of 2, as a length in her finished model. Kind of interesting. You can do other things. Instead of making a triangle, you can make a loop in the strip, put one end through the loop, and when you pull the ends tight, you end up with, theoretically, a perfect pentagon. And this one has some extra cool features in there. If the side length of the pentagon is 1, then we get this. Sorry, the contrast isn't great, but 1 plus root 5 all over 2 on the long diagonal, also known as the golden ratio. I've cheated a little bit because the width of the strip isn't actually 1. There's some constant factor, but the golden ratio is still there in the model, and I think that's kind of cool. But most people don't start with a chip bag crisp packet. They start with a square or a rectangle of paper. But we can still do some cool things with very, very few folds on a piece of paper. A lot of models start like this. You fold in half, you crease, you unfold, and from a side length of 1, we've managed to construct, excitingly, a half. Woohoo! Thank you. You might think that's not so interesting. We've also constructed new points where the crease meets the edge of the paper, and we can use these new points we've constructed as anchors for further folds. For example, we can put the corner to one of our new points, like this, and now we've constructed some new distances. We get an 1/8, we get 3/8, 5/8, 1/6, and 2/3 along the top, and all of the complements with a slight length of 1, like 5/6, 1/3, and so on. So a whole host of new fractions have come out of here, and also some new points. And we can now use those new points as anchors for further folds, and we can keep going like this. And just by unfolding and refolding in this manner, a researcher called Haga actually showed we can construct any rational fraction we like, as long as it's less than 1. So that's brilliant. We get all rational numbers we can construct using origami. But you may think, hold on, you just showed us root 2 and the golden ratio. Why should I be excited about fractions? And really, the question we should be asking now is, what can we do with origami? What's the limit of what we can construct, what we can calculate, and maybe more pertinently, what can we not do? So let's try and formalize what we're talking about here. What exactly is a fold? What are we allowed to do in origami? What are we not allowed to do? So as with any mathematical or scientific structure or system, we're going to start with the fundamental indivisible operations, our folding axioms. I'm going to go through some now. If we have 2 points, there are 2 things we can do with them. We can fold through the 2 points, like this. I'm going to call that axiom 1. We can also fold 1 point onto the other one, like so. And we'll call this axiom 2. We've managed to create some lines here in the creases. We also have some pre-existing lines in the edges of the paper sometimes. And if we have 2 pre-existing lines, we'll say that axiom 3 is that we can always fold one line onto the other, creating a new crease in the middle. Axiom 3 is actually a little special because there's more than one way to do this. By that I mean there's a second fold that achieves the same thing, puts one fold onto the other, one line onto the other. If it's not clear why that is, it's because I've cheated a little bit for the second time this presentation, if anyone's keeping track. You kind of had to zoom out to see what's really going on here. The lines intersect somewhere, and where they do, we can fold the other way. So 2 solutions, unless the lines are parallel, in which case there's just one. But axiom 3 can be done in multiple ways in general. Using these axioms, we can already start to perform calculations using paper folding. I'm going to show you a quick addition. We're going to say that variables or inputs in our origami calculations are going to be distances on the page, on our infinite theoretical page. So some distance A and a distance B, they can be anywhere. I've just chosen some random points on my slide. And the way we add them together to construct the distance A plus B is first we use axiom 2, point onto point. And we mark where it lands on the other side of the fold using more folds, no pens allowed. And then we fold through the 2 points of B, that's axiom 1, to sort of extend the line beyond the limits of the B line segment. Then we do axiom 3, line onto line. And we're already done. This gives us the distance A plus B. Addition conquered, great. Axiom 3 has 2 solutions sometimes. The other one simply goes back along the line segment B, and we get subtraction for free as well. But there's more. There are more folds we can use. Axiom 4 says we can fold through a point such that the fold is perpendicular to another line, like this. And you might say, hold on, perpendicular folds, where did that come from? Why are we just allowed to do that? The way this works is that we just simply align the line with itself on the other side of the fold. This is something that's done quite often in origami models. It's allowed. And moving on quickly to axiom 5, we start to see some more interesting theorems, interesting ideas coming into the axioms. We can fold a point onto a line such that the fold goes through another point. This one, we're introducing something new in that the points are performing different roles. It matters which point is which. So I've marked them differently. The dot on the left-hand side of the line has to go onto the line, and the fold has to go through the cross on the right side of the line. And a fold might look like this. And it turns out axiom 3 isn't actually that special because this one also has more than one solution. We can fold down there instead. This one is actually quite interesting, though, because it's not always true that we have 2 solutions, or even one solution. If you imagine that the cross is instead down here on the left somewhere, then you might look at this for a while and convince yourself there are actually no folds that go through that cross that put the point onto the line. The point's kind of too far away. You can never get it there. And if we move the cross around, we find that if it's in this shaded area, there are 2 solutions. If it's in the bottom left unshaded area, there are no solutions. And if it's on the boundary, we get one solution, one fold that works and can perform Axiom 5. That is a parabola, it turns out. For any parabola nerds, the point and the line are focus and directrix. So we have a folding axiom that has either 0, 1, or 2 solutions based on the result of a quadratic equation in the parabola. Hopefully, some of you are excited by that. But there is more. Another fold, which we call Axiom 6, is really special. It's kind of the big one. It's got its own name, the Belloc fold, and it's named after Margherita Belloc, an Italian mathematician, who didn't discover the fold, but is generally credited as the first person to realize its potential and its power in computation and calculations. It says we can put one point onto a line and simultaneously a second point onto a second line. Again, it matters which point goes onto which line, so the dot goes onto the single line, the cross goes onto the sort of thicker double line. Hopefully that comes out on the slide. And it might look something like this. Cool. But, as before, there is more than one way to do this. This time, I really don't think it's clear what a second solution fold might look like. You can even take a second. I'm not going to ask for audience participation because you'd just be sort of gesturing, drawing lines in the air. I don't think that would work. But in your head, try and think, how else could we fold such that the dot goes on the line, the cross goes on the double line? The reason I think this is so tricky is because they sort of have to go in opposite directions across the fold. This is allowed. Mathematically, there's no difference to saying point onto line versus line onto point. So we can fold in both directions like this. And in fact, one of the reasons this is so special is it's not just 2 solutions, there are actually 3. There's a third fold that does it. And if we put all those lines on the page at the same time, maybe starts to peek out through the mist. In fact, the parabolas are back again. And this time the solutions are, weirdly, the lines that are tangents to both parabolas. So there are 0, 1, 2, or 3 folds that we can do to accomplish what we want, depending on whether the parabolas intersect, how they're aligned relative to each other. So yeah, very cool, Axiom 6. There's one more. Unfortunately, this one's not quite as interesting as the last 2, in my opinion. We're sort of winding down towards the end of our list of axioms. Point onto line, parallel to a second line. Generally one solution to this, unless the lines are parallel. Sometimes there are no solutions. So that's our full list. I didn't come up with it. It was initially enumerated by a French mathematician, Justin, and then independently rediscovered by 2 Japanese researchers, Huzita and Hattori. And you'll sometimes see various combinations of their names appearing on this list of axioms. But it wasn't until Robert Lang came along and proved eventually in 2010 that we knew there were no other axioms. This was a full list of fundamental operations in origami on the plane using one fold and that there were no others. Anything else can be expressed as a combination of these 7 operations. Cool. We've got our basic building blocks. What can we do with these? And how do we explore and research, try and navigate our way through the landscape of what's possible in origami? It is probably a bad idea to try and do it in person with a piece of paper. We are all fallible humans, I assume. Sorry if anyone's not. So we are programmers. We want to do this using code. So introducing Origametry. That's Origami Geometry. I mean introducing. This is brand new, uploaded to PyPI just before this conference for everyone to play around with it. And it works like this. We can import a fold function, and this is axiom 2, point onto point. We simply pass the 2 points as arguments to the fold, and it returns the line. There's the crease between them. This is axiom 6, the Belloc fold. We give it point 1 onto line 1, and then pass a 3rd and 4th argument, which is a second pair of thing onto thing. So we can just keep going like that. We do perpendicularity. like I suggested earlier, by just folding a line onto itself. We just passed the line twice. And folding through a point is equivalent to folding a point onto itself. This is the same representation that Justin used when he first enumerated the axioms. A little side note. Cool. Let's see it in action. Let's redo our addition algorithm using Origametry. First, going to just define a couple of points as our initial lines, and I've chosen some that make the numbers nice. So we have a distance of 5, distance of 13. It's not really to scale, but whatever. And we do our first operation. I'm now going to call the reflection C just so I have some variable names in the Python code. And it looks like this. Fold point onto point, and then we look at the reflections, which is a function that also comes from the library. We then fold, kind of extend the line through the B line segment, looks like that, through one point, B1, and through another point, B2. And finally, we fold line onto line, which I'll call D. This time we actually need to define the line C because we didn't have that yet, technically. And we fold line onto line, name the reflected points D, and hey, we're done. The distance is indeed the sum of our initial inputs. So we've got an algorithm that works now in Python code that simulates folds, and it's not totally abstract. You can just repeat these folds with a real piece of paper. It works to some human degree of error. And we don't have a huge amount of time to go through all the algorithms that I really want to, so I'm just going to jump straight to the big one, solving cubic equations. I mentioned earlier, actually no, I don't think I did, I think I forgot to, but the Baylock fold, finding tangents to common tangents to parabolas is equivalent to solving cubic equations. And I don't mean that in some abstract, obscure mathematical definition of equivalence. We really can find the roots of cubic equations using origami. You can do it with a piece of paper if you're brave. I would suggest simulating it. We've got these 4 variables, A, B, C, and D, just like we had 2 variables for addition. We just have a couple more line segments somewhere on our infinite plane. And I'm going to take an example here. Again, I've chosen numbers that make it nice, but it should work with anything. And it goes as follows. This is very awkward and a little bit obscure, but I just want to show you that it's possible. I don't expect anyone to follow along fully. But we take our coefficients, we chain them together end to end, just like we did with addition, but instead of putting them along a straight line, we're going to turn at 90 degrees each time. Like this. There's our x cubed coefficient, x squared, x, and our constant. We're then going to scale everything down, so the starting line is 1. And that may seem like a weird thing to do. But there is no concept of unit length in origami, we just have ratios. So we can simply redefine that first line segment to be 1. That was easy. And we also get the same solutions, because the equation is equals 0, so we can just multiply through by any constant we like. The solutions are the same. So this works. It's safe. You may ask, what if one of the coefficients is negative? So let's actually do that. I'm going to change the +2 at the end to a -2 and see what happens. Goes the other way. Importantly, we're not turning right at the end. We're turning left and then going backwards. That is a very important distinction when we're constructing this, interestingly enough. Okay, we do a bunch of folds now. I've skipped over some of the details. We know we can put things end to end. We know how to do perpendiculars, so skipping over that bit. Now it gets interesting. We do a couple of axiom 1s through 2 points, mark the new points. We do a couple of axiom 4s, perpendicular through a point, to get some new lines. And finally, it's time for the big one. Point onto line, and second point onto second line. The Baylock fold comes in. This might look really weird. Yeah, it's kind of magical. I wouldn't try to understand it unless you really want to. And if you want to, feel free to go and look it up yourself. I don't have time to explain it all now, but it's a deep rabbit hole, but very fun. And if you come across something called Lil's theorem or Lil's method, you're on the right track. Axiom 6 is tricky to deal with, so let's give it to our Python library, Origametry. and see what it makes of it. We do our point onto line and the second point onto second line. And I had to kind of put everything in, plotted it in matplotlib, lib. And these are the lines that our library gives us. These are the three folds that can put the points onto the lines in the right way. Mapping back to my sort of hand-drawn, not-to-scale diagram, we're pretty much done. We just look at where these lines now intersect this horizontal, and the horizontal distances from our starting point, 1/2, 1, it's minus because we're on the left, and 2. -2, -1.5, and that's it. We have constructed distances corresponding to the roots of our cubic equation. And if you don't believe me, here's a proof by Wolfram. So it's a little small, but it's the same cubic. We get -2, -1.5. Like I said, this works for any cubic equation. It solves the general cubic, and that's great. That's really powerful. What about quartics and higher order polynomials? The answer is, unfortunately, with our 7 axioms, we can't solve these. But there's more that origami can give us. I did say the 7 axioms were complete for one fold at a time origami, but origami is more powerful than that. Going back, you might remember my little pentagon. When I made that, I didn't use any of the axioms that I've already covered. When I pulled the ends tight on my little knot, I was creating simultaneously 1, 2, and 3 folds, all aligning at the same time and creasing them all at the same time. You couldn't create one without the other ones to help it along. So we're actually stepping up into the world of multifold origami. Multifold axioms exist, and using these, we get quartics, general quartics. We get quintics. And this is my personal favorite moment of the presentation. ... It's been shown, if I understood the paper correctly, it was very complicated, that we can solve any order of polynomial we like, and we get all the real solutions using origami folds. I really would not recommend trying to do this with a real piece of paper, because aligning more than 2 things at once gets really difficult, really tricky, and you've got to find all 7 ways to do it or whatever. So let's stick with computer simulations for this stuff. Any order polynomial, that's fantastic. What else can we do with origami? I'm going to leave the computation as a kind of proper number analytical stuff for now and look into mathematical proofs. This is a little neat trick I want to show you. We can prove that root 2 is irrational using origami. And we just need 2 folds. One like this. It's a very common way to start an origami model. And then we fold 1 layer from the right over onto the diagonal here. And we get a 1, 1, root 2 triangle. The proof then goes as follows. If root 2 is in fact rational, i.e. the ratio of 2 integers, then let's take some integers with that ratio. Let's take the simplest ratio, in fact, so the smallest integers it works for. We'll call them x and y. Again, I've chosen some bad colors, I think, but that's x along the top, x down the right, and y along the diagonal. If we have these integers, then x here means that this distance is also x. We just folded it over there. The entire diagonal is y, so that's y minus x. By similar triangles, that equals that, and that equals that. The thing along the top is all x, so this bit is the difference, which is 2x minus y, and we've constructed smaller integers with the same ratio. But we assumed that x and y were the smallest integers it worked for, so contradiction. This can't be possible. Our initial assumption was false, therefore root 2 cannot be the ratio of 2 integers, therefore root 2 is irrational. Thank you. I didn't come up with this, but standing on the shoulders of these guys at the bottom. They also claim they didn't come up with it. It's probably been known for a very long time, but this is the first reference I could find. Sorry if the references at the bottom can't be seen by people at the back if you're looking over people. I'll show them all at the end as well. So yeah, mathematical proofs, and we only needed 2 folds to do that. Kind of cool. All right, we have time for one more. Can we do pi? Can we calculate or at least approximate pi using origami? I'm not going to say yes or no at this point. I'll maybe let you decide whether this is valid or not. But I just want to draw attention to something that I thought was really cool when I heard about it. Brittany Gallivan, in 2002, folded a very, very long, very thin strip of paper in half in the same direction 12 times in a row, totally busting the myth that 8 times was somehow some universal constant limit. I don't know how many people have heard that. Some people say 7. But yeah. Yeah, she said that's totally not true. She did 12. It's really a showing off. But in 2001, I believe, before doing that, while she was still at school, Gallivan derived an equation to find the length of paper required to fold the paper n times. And the equation is quite a lot more complex than you might expect. It looks like this, where L is the length of paper that we need to do n folds. T is the thickness of our paper. So we're stepping really far away from the theoretical world. We're back in the real world where paper has thickness, and we're trying to break some Guinness World Record or whatever. And what the heck? There's a pi there. What on earth is that doing in our equation for just dividing something in half a couple of times? Well, Galvin wasn't crazy. That is actually correct. And the reason there's a pi there is because if you look at the cross-section of a folded piece of paper, you get your paper lying across itself a couple of times. You also get these circular arcs on the edges. So if you have a piece of paper, you fold it in half a bunch of times, and then you measure the excess paper that is needed for these folds on the side, you can approximate pi using Gallivan's equation. So Matt Parker, next Pi Day, another approximation method just dropped. Yeah, so all sorts of stuff you can do with origami. That's it for the presentation. These are the really, really smart people who did all the work before me. And that's me at the end. So thank you all. Please do have a look. There's my GitHub. It was my first attempt at actually uploading a PyPI package. So if you have experience with that, please do come along and help, drop some PRs and maybe give some pointers. And if you find me in the hallways, just talk to me about origami. I'm a lifelong fan. Show me what you've made. And enjoy the rest of the conference. Thank you. Am I still on mic? Cool.
Yeah.
Do you want to bring the mic over? Oh, okay.
Hi, Ali. That was a good presentation. That plot, matplotlib that you've shown, just a simple question. Is that something you've done manually, or that's part of the library that you've created?
I'm just going back to the slide.
So, in other words, is there a plotting function inbuilt into your, this, exactly.
I really wanted there to be a plotting function. I had to do this manually. It does spit out the line in terms of a general line equation, coefficients of ax plus by plus c equals 0. So it gives a representation for a line if you need to plot it. You currently have to do it manually. Open an issue for that, though.
No. Okay, thank you.
Yes. But yeah, that's like next steps for the library, I think, is actually start to visualize things properly.
Cheers.
Anyone else? the microphone on over there?
I'm sure everybody else knows, but how long was the paper?
How long was the
Strip, folded
the
12
paper
times.
strip? I have a number in my head, and it might be completely wrong, but yeah, it was in the order of, I believe, kilometers. 1 unit, thank you, yes. You're quite right. It was incredibly long, and I think it was provided specially by some paper factory somewhere on special order. But yeah, I believe it was hundreds, if not thousands of meters long. I don't know what that is in feet, I'm afraid. 2 feet.
Hi. Thanks for the talk. It was very interesting. You mentioned you could use the folding for all order polynomials for the real solutions.
Yes.
Is there any work looking to extend that to infinite order polynomials? Like if you had a Taylor series of all functions?
I guess that would mean making infinite folds at the same time.
Is that possible?
Yeah, I'm not the right person to ask about that. I do not know enough about the topic, about what that would represent, because you definitely could make infinite folds at the same time as some sort of repeating pattern, maybe, and collapsing your piece of paper at once. But it wouldn't be quite the same. What I'm calling folds are really alignments of one entity with another entity. So performing that many alignments simultaneously might be, at least computationally prohibitive. But theoretically, I don't know.
There's a last one.
Good question.
Sorry, there's a last. Thank you very much, Alan.
Okay.
We'll give a little
Thank you,
bit of
everyone.
applause.